Okay, let's start. Today we will look at the fundamental theorem of calculus, which is almost a miracle because on one hand you are calculating areas, on the other hand you are mechanically taking derivatives of functions, and somehow these two turn out to be related. Okay, so the topic is the fundamental theorem Okay, so for this, we start the continuous function. Okay, so first of all, what does this say? On one hand, we calculate areas. Areas under a curve. Okay, so on one hand, you have this process. On the other hand, you have taking derivatives of functions. Okay, so they look like two different concepts. It turns out that fundamental theorem of calculus, okay, so it relates these two to each other. Okay, so the first part, okay, so first part is the following. We start with a continuous function. Okay, so let f be a continuous function on an interval on AB. Okay, so kind of closed and bounded interval. Define a function g of x as the integral from a to x f of t dt for all x in AB. Okay. So the picture of this will probably be something like this. Okay, so this is in this notation, this is the t-axis, this is y-axis, and you have this curve from A to B, y equals f of t curve. Okay, and you have an x here somewhere. Okay, so you have x here, and you calculate this area. So far, we don't know how to calculate this area technically, but we know that we can approximate it by Riemann sums, and if the limit exists. And we know that if f is continuous, the limit always exists. So g of x is this area. Okay, so g of x is this area. In my picture, the function is positive. So as x increases, the function increases, but it can be negative. So sometimes the value increases, sometimes it decreases. Okay, so the punchline of the theorem is that this function is now differentiable. Then g is differentiable. And moreover, g prime x is equal to f of x. Okay? The value of f at that point tells you how fast the area is increasing under the curve. Okay, so first of all, let us prove this. Okay, so proof. Well, we know the general definition of derivative. Okay, so you see that this is one of those cases for which we don't have a rule yet to find the derivative of such a function. After this theorem, we know immediately that if you have such a function, the derivative is this. Okay, but at this time, this is not like x to the power n or 1 over x or sine x, cosine x. So we don't, from our repertoire, write down the derivative. We have to use the definition. Okay. So by definition, g prime of x is equal to limit as h goes to 0 of g of x plus h minus g of x over h, if the limit exists. Okay? If limit exists. Okay? So we write this expression, we try to understand this expression, and check if the limit exists when h goes to 0. Okay? Okay, so let's, by definition, let us look at this x plus h. X plus h is instead of, this is the only place where we see h. So g x plus h is equal to, or let me write minus g of x is equal to integral from a to x plus h f of t minus integral a to x f of t dt. Okay, now we use properties of integrals. This is integral from a to x plus h. Okay, so I can write it as integral from a to x f of t dt plus integral x to x plus h f of t dt minus this thing a to x f of t dt. Okay, so we see that these things cancel nicely. Okay, and we have integral x plus h over of the function f of t with respect to t. Okay, so now we try to understand this. Okay. So note that now we use the assumption that f is continuous. Okay, so what was one of those useless looking theorems about continuous functions on a closed and bounded interval? It always has a minimum and maximum. Okay, f continuous on interval x plus h, assuming now h is positive. Okay, we know that h is different than 0. H is either positive or negative. If h is positive, this is the interval. If h is negative, then I have the interval is x plus h x. Okay, because h is subtracting something. So the sign of the increment h does not matter much. As far as we are concerned, it's a closed and bounded interval. F is continuous on a closed and bounded interval. So must have a minimum and and maximum Okay, it must have a minimum and maximum on this interval. Okay. So let us say that the minimum and maximum occur at certain places. Say u, v in x plus h are such that, so maybe I should put sub h here because they change as h changes. And no matter what h is, that's the crucial part of this. No matter what h is, how small or how large, there are always 2 points here where f takes the minimum and maximum. Say f of uh is equal to minimum of f of t. T is in x plus h. And f of vh is maximum of t in x plus h f of t. Okay? So, well, we have also now one of those, again, boring-looking properties of integrals. Okay? So if a function is, okay, so another property, another boring property. If I have two functions, let's use some scientific-looking expression. If alpha x is less than or equal to beta x on some interval, say CD, then integral of alpha x dx on a b is less than or equal to integral of beta x. Okay, so this was one of the properties. We apply it to this thing. Apply to f of UH less than or equal to f of t less than or equal to f of VH on, what is my integral? X plus h. Okay, so these things are not part of the proof. I'm just reminding you, because after you do this, you immediately write the next inequality, but I'm reminding you why we write this. So I apply it to this. My interval is x plus h f of UH dt less than or equal to x plus h f of t dt less than or equal to this thing again. Okay, I'm integrating with respect to t. I look at this thing. This is a number. Okay, so that's the maximum of this function. This is a number. Again, another property of integrals. This comes out. This number comes out. F of UH integral x plus h dt. Okay, I'm integrating the number 1. So this is this minus this. This is equal to h. Okay, so this minus this h. So this is h times f of UH. Okay, so I do the same thing here. So no need to write this two intermediate steps. I'll get exactly the same thing here, f of VH h. Okay, so what I have is the following thing. I have this guy in the middle, less than or equal to this thing, and larger than or equal to this thing. Okay, and this thing in the middle is equal to this thing. Okay, and this thing is over here. So what I am missing is dividing this by h. Okay, so we'll divide it by h. Let's do that here. Okay, so putting these together. Okay, so I take this one. So let me take the limit later. I take this one. G of x plus h minus g of x divided by h. Okay, so this thing, this is equal to this. So I'm dividing by h. So this is equal to integral x to x plus h f of t dt, and I divide it by h. Okay, so this is equal to this. That's from what we did. And now in the last line, using these equations, I'm dividing this by h. I assume that h is positive. So when I divide all sides of this inequality by h, the sign of the inequality does not change. If h was negative, I go and check what would happen. The interval would change. Okay, so here the integral would change. I divide by h. H is negative, so sign of the direction of the inequalities would change, but it would not change my overall idea, because the integral in the middle divided by h would be bounded by on the right or on the left by these two numbers, because when I divide by h, this thing will disappear. So this side, when h is positive, is f of vh, and this side is f of uh. Okay, so this is what you get when h is positive. If h is negative, the only thing that will change is that these will change places. So I again have this thing. So now I take the limit. Okay, so take limit as h goes to 0. So take limit as h goes to 0 of everything here. Okay, so what do we get? When h goes to 0, okay, so we check here on, so we have something like this. Okay, let's start with this. On x plus h, we have the following thing. This is x plus h. UH is somewhere here, VH is somewhere here, or maybe their places are different. I don't care. When h goes to 0, so this side moves in this direction, and eventually this side coincides with x. Okay? So it forces these two numbers coincide with x. Okay? We are squeezing. This side is staying fixed. I'm moving this to this side. What I know about these two numbers is that it is always inside this interval. So they are squeezed to x. We get UH and VH go to x. Okay? F is a continuous function, so another boring property. This was boring when we did it because there was no reason to observe all these totally trivial looking properties, but they are crucial here. Now I'm taking the limit of this when h goes to 0. That's equivalent to taking the limit when u sub h goes to x. F is continuous, so I can push this limit operation inside, and I can just say f of limit as uh goes to x. So the result is f of x. Okay, so this becomes f of x in the limit. Less than or equal to this thing, I know that if I take the limit of this, if the limit exists, it's going to be g prime of x. And again, this thing goes to x, f is continuous, so f takes that value, f of x. Okay, so this shows me that the limit exists. It is between f of x and f of x, which is another way of saying that the limit is f of x. Okay, so this shows that g prime of x equals f of x. How do I know the limit exists? Squeeze theorem. Okay. This operation, I don't know whether its limit exists or not. It is between these two expressions. These two expressions both converge to f of x. So by the squeeze theorem, this middle thing, whose limit I'm trying to check, exists and is squeezed in the middle to f of x. Okay, so that is, as we write since the time of Euclid, QED. That which was to be demonstrated is demonstrated. That's the Latin for that. Okay, so this, in a surprising way, this gives us a relation between derivatives and areas, but we will exploit this. At this point, we still don't know how to calculate areas, but let me do one or two examples to get used to this notation. Okay, because we will be needing these things. Okay, so examples. Okay, so let, for example, g of x equals integral from 7 to x cubed cosine of 1 over 1 plus x squared d. Okay, let's see how I can change this in the cheapest way. Just to confuse you, let me call this t and call this x. Okay, now what is g prime of t? Okay, so at first this looks very complicated, time consuming, because at first you feel that you are going to take the derivative of this whole thing, which is not difficult, but of course nobody likes to write these things step by step. But this is an integral. The fundamental theorem of calculus says that you evaluate this object at this point, that's the derivative of this. Okay, so we take this object here. So evaluate, okay, not differentiate, evaluate this at this point at t, that is g prime t. Okay, so that's what the fundamental theorem of calculus is saying to us. So g prime t is just t cubed cosine 1 plus t square. Okay, so that's it. Okay, so let me see. So I said, let's do one more example. Okay, so 1, 2, g of x this time equals integral from 0 to x. Let us write a function of t here. 1 plus tangent cube t square over secant t square plus 1 plus 7 dt. Okay, so just to scare you at first that you have a rational function of several trigonometric functions combined with polynomials. What's the derivative of the integral of this? Once you say what's the derivative of integral of this, you are not going to take any derivative. You just evaluate this. Okay, so g prime x. You evaluate this at the top point at 1 plus tangent cube x square over secant x squared plus 1 plus 7. Okay. Okay, so far so good. It looks another useless calculus theorem where you can show off your ability to take derivatives, but what is it good for? Where do we use this in real life? Okay, so that takes us to the second part of the fundamental theorem of calculus. So let me see if I'm following my plan. Okay. Ne oldu, kaçıyor musun? One part of calculus was enough for her. She cannot stand the second part. Okay, so now we come to the second part. Okay, so second part. Again, we start with the continuous function. Function f of x on a closed and bounded interval. Okay. Let f of x be another capital F be a function, a differentiable function such that be any differentiable function such that f prime of x is equal to f of x on a b. Okay, so from what we did so far, when we say any differentiable function, we know that it's not a big deal, because if you find one differentiable function whose derivative is equal to this small f, all other differentiable functions with the same property comes with the same f plus an additive constant. Okay, so this is saying that don't care about the additive constant, just pick one of those things. Then, so this is where this is useful in everyday life. Of course, I'm talking everyday life of an engineer. Normal people don't use this anywhere. Okay, we are not normal, so this is our everyday life. F of x dx is equal to f of b minus f of a. Okay, so this now gives us a method of calculating exactly the value of a definite integral. We don't need Riemann sums. Riemann sums are there to develop the theory, to show that the theory is sound and such things exist. Okay, but now we can say goodbye to Riemann theorem. It helped us, but now we have a new friend. If we can find an antiderivative, this is exactly the value of the definite integral. The bottleneck here is this part. If small f is a simple function, you immediately guess what the capital F will be. When f is small f is not something that is in your repertoire, then it's difficult to make a guess. So the rest of this chapter and the next chapter, we will look at techniques of dealing with small f so that we break it into smaller parts where you recognize the antiderivatives of the smaller parts, because taking derivatives and antiderivatives are linear. Okay? So if f is the sum of two functions and you know the antiderivative of each of them, so then an antiderivative of this one is the sum of the antiderivatives of the small ones. But if f is sum of two functions whose antiderivatives you recognize, then we again call f a simple function. Okay? It's the problem is when f is a really complicated looking function, you know that it is continuous, so you know that an antiderivative exists. Okay? An antiderivative exists because of the first part. Okay? If you have a continuous function, there is always an antiderivative. In this case, g is the antiderivative of this function. Okay? So no matter which continuous function you have, there is an antiderivative. The problem is we don't know how to write it down other than the integral sign. Okay? In order to obtain the exact value, you have to find a formula for an antiderivative. Okay? So this part is the bottleneck. So the next chapter, I think, is techniques of integration, is to play with small f so that it will come up as parts, as summation of small parts, and you know the antiderivative of each of them. Another thing you have to pay attention is that this process always stops at a place where you have to use your own repertoire of antiderivatives. Okay, so you should know a few antiderivatives because this doesn't go all the way down. It stops somewhere, and then at that point you have to pick it up. You must say that, oh, okay, this is cosine, so its antiderivative is sine. Okay, so let us see if we can prove this one. It looks useful, so let us look at the proof. After this one, the proof is surprisingly easy. That was the bottleneck. Okay, so here you see in the proof of saying that the derivative of this is inside, we had to use all the properties of continuous functions. Now, proof of this uses only the first part. Okay, so let g of x be f of t. Okay, so f of t dt from a to x. X is on a, b. We know that, so we know already g prime x is equal to f of x. Okay, so this is one antiderivative. Then any antiderivative f is of this form, g of x plus a constant. Okay. Here so here again, x is in the interval a, b. Okay. Note, however, that g of a is equal to 0 because integral a to a of something dt, this is equal to 0. Okay. So we calculate this side. Okay, so that's a big surprise. You were thinking that I would start from this side, work my way through, break my back, and get this side. Well, I surprise you. I start from this easy side. Okay, I write f of b minus f of a. Okay, I know what f is. So f of b is g of b plus c minus, I look at f of a. F of a is g of a plus c. Okay, we just observe that this thing is 0. Okay, I have plus c minus c, so these go, and I obtain g of b. Okay, and what is g of b? I just put x equals b here. This is a to b, f of t dt, QED. Okay, so this is a very useful theorem, but with a little hitch. As I said, given f, we have to guess a formula for big F. Okay, so let's do a few examples again. Now we'll start with the simple examples, those examples which do not need any techniques, so that we make sure that we know by heart antiderivatives of some simple functions. So examples. Okay, so the first one, let's say, integral from, well, the numbers are not easy, 3x cubed dx. Okay, so for the first one, let me do this in detail. What goes on through our mind in half a second is the following. We look at this thing, so let me write it in, I don't know, let's write it in. So this is our f of x, okay? So we find f of x such that f prime x equals f of x. But this is x cubed, okay? So we guess that f of x must be x to the 4. So it must be x to the 4 because when I take the derivative, I'll get x cubed. But when I take the derivative of this, 4 comes out. I don't have 4 here. So I put 1 over 4 to kill that extra 4. Okay? So derivative of this is now 4 times x cubed divided by 4. So I just get x cubed. Okay? Well, I can write plus a constant here. Just to be on the safe side, I write this. But since I'm going to use this formula, you see the constant of this will be canceled by the constant of this as it appeared even in the proof. Okay? So I don't need this constant if I'm doing definite integrals. Okay, so I take this over here. I take this over here. I have, so here I say f of x is equal to 1 over 4 x to the 4. So I have f of 3 minus f of minus 3, minus 2. Okay, so this is 1 over 4, 3 to the 4 minus 1 over 4 minus 2 to the 4. So whatever that number is, okay, you calculate that. That's the answer. Okay, so notation here, some useful notation. Well, all notations are useful, but this is very useful. So let me write very useful notation. F of b minus f of a. Traditionally, we write this as f of x from x equals a to x equals b. Okay, so you subtract this from this. This is the notation. So sometimes you write f of x a to b if x is understood. Sometimes f has several parameters in it. You are working with only one parameter, so then you have to specify which parameter you are using. Okay. So this we could write 1 over 4 x to the 4 from minus 2 to 3. Okay, so this is the notation we use for these things. So in particular, for the general thing, we have integral from some number, let's say from 2 to 5, x to the n dx. Okay, so this is equal to when n is different than -1, because you see what I did here is take this power, add 1 to it, and take its reciprocal here. If n is -1, when I add 1, I get 0. I cannot take its reciprocal. Well, I can always take its reciprocal, then it leads to all sorts of useless, funny things. So when we say you can't do it, it means that you can do it, but then I will not listen to what you do after that. Okay, so this is 1 over m plus 1, x to the m plus 1, from this number to this number. Okay, so when n is equal to -1, then an antiderivative for 1 over x is logarithm x, and we will formally do it later. Okay, so so for example, we have to cosine, let's say, okay, so let's take another example. Integral from 1 to 2 cosine x dx. Okay, and antiderivative for cosine is sine x from 1 to 2. The only nice thing about integrals is going from here to here takes some time, so takes some effort, okay? But once you write it down, it is mechanical. Just take the derivative of this thing and check if you get this one. Okay, so solving the problem is difficult in integrals, but checking if your answer is correct or not is mechanical. If you are claiming that the derivative of this is equal to this, then you just take the derivative of this yourself before somebody does it on the exam paper, and you check if you found the antiderivative correctly or not. So for example, if you had sine x dx from some number to some other number, and if you write, you know that sine and cosine are antiderivatives of each other, then you check derivative of cosine. Now you remember there was a minus sign, so you put that minus sign here. Okay, so that's why sometimes we use this parentheses. Okay. Okay, so there's one more remark I have to make. On these things, observe that we always said start with a continuous function on an interval. So in particular, the function is defined everywhere on that interval. If you have 1 over x, so these things happen quite often. So I need to make a note of this. So beware, however, f must be defined and continuous on the whole of the interval a, b. Okay? So here you see defined and on the whole are unnecessary words. If I say f is continuous there, obviously I mean that first of all f is defined everywhere. Moreover, it has an extra property that it is continuous. But now I'm emphasizing this. For example, f of x equals 1 over x is not defined on all of -1, 1. There's only just one point where it fails, but the theory does not cover that. The theory does not say that I will forgive the function if it only behaves badly at one point. Okay? So if you have something like this, integral 1 to 1, 1 over x dx, this does not exist. Okay? In fact, the graph is something like this. Okay, so 1 over x on one side goes like this, on the other side goes like this. If this is -1, this is 1, then you are talking about this area. It turns out that this area does not exist. Okay, so you can take x squared, x cubed, you can check what happens. Those things will do later, and that will be useful at the beginning of next semester when we do infinite sums. Okay, so those things, if the function goes to infinity, then you have to approximate what happens and take the limit. But those things are called improper integrals. We'll do them later. Okay, so as far as we are concerned, in order to use the fundamental theorem of calculus, you must make sure that first of all the function is defined everywhere. Okay, then another example. Okay, so let me do Leibniz rule. Okay, so this is something that comes up again very often in our calculations. You see, when I'm taking the derivative in the first part of the fundamental theorem of calculus, there was an x on the top of the integral. I integrate from a to x. What happens if I integrate from a to x squared? Okay, so that's a different function. And then our feeling is that if the integral from a to x is differentiable, then integral a to x squared, well, it doesn't look very different. It must be differentiable. But what will be its derivative? Okay, so Leibniz rule. So let us say, so what notation I am using? I am not using any notation. Okay, so let's say phi of x is equal to from a to g of x, f of t, d of t, x is in, okay, so x is in some interval. Let me not be very precise, because then I have to talk about the range of this also. Here, f is continuous, g is differentiable. So we assume that the numbers, the range and domain of the functions match, so the integral makes sense. Okay? So for a particular x, we are talking about an interval from a to g of x. F must be continuous and defined everywhere on that interval. So we are assuming that these nice conditions hold. Okay, so the question is, what is phi prime of x? Okay, so that's the question. Okay, so again, this is one of those places where we have to use the definition of the derivative. Okay, so phi prime of x equals limit as h goes to 0 of phi of x plus h minus phi of x over h. Okay, so now that we know this, let us look at phi x plus h minus phi of x. This is integral from a to g of, wherever I see x, I'll put x plus h. I see x only here, so this is x plus h, f of t dt, minus integral a to g of x, f of t dt. Okay, so I write this thing again as follows: integral from a to g of x, f of t dt, plus integral from g of x to g of x plus h, f of t dt, minus, I write this, integral a to g of x, f of t dt. Okay? So I don't know if g of x is less than or equal to this or not. It doesn't matter. So that's why we said that we can shift the places of these things. That's why we didn't insist that when we write an integral, a definite integral, the number here must be less than the number here. Okay? So we developed the theory nicely without making such redundant assumptions. So that becomes useful here. I don't care if g of x is less than this or not. I can use the property that integral from some point to some point, and then from some point to this some point. If I add them, these things touch each other, so I end up integrating from this point to this point. Okay, so this one. So I can algebraically write this, and these things cancel each other, and I have this. Okay, so at this point, choose a f such that f prime x is equal to small f of x. Okay, so a fundamental theorem says that such a function exists. Lots of such functions exist. All of them, well, it's actually the same function, but you keep adding any number you like. Okay, so let's see what we are doing now. Then I want to write this thing. Okay, so now I want to divide these things. X plus h minus phi of x over h. Okay, so this is equal to 1 over h. I have this g of x, g of x plus h. Okay, f of t dt. Okay. Now, well, maybe I didn't write it here, but now I want to take the limit of this, but let us see what this means. Okay, so I have this thing. Okay, so continuing with this, since I'll remind you something, let me use a different color. Okay, so well, black. This black was nice. Okay, so here, note that f of x, or maybe let me use something else. F of u is equal to integral from a to u f of t dt. Okay? This was the definition. Then f prime u is equal to f of u. Okay? So here, instead of u, put g of x. Okay, put g of x. So what do we have? We have f of g of x is equal to integral from a to g of x f of t dt. Okay, so now does this thing look like what we have over there? Okay, so it does. So let us do that. Using that, I can write this as follows. Equals 1 over h is here. Okay. So this thing, first of all, I write from a to, okay, I start from a to g of x plus h, f of t dt. And then, or okay, let me write it this way. Algebraically, it will look more convincing. Okay, I start from here, g of x to a. Okay, I'm just putting a there, f of t dt plus from a to g of x plus h, f of t dt. Okay, so I'm again using one of those properties of integrals. I integrate from here to here. This here is the same as this here, so they just glue and give me this one. Okay. Now at this point, I use the other property. I can turn this around, but I have to put a minus here. Okay, so I do that. 1 over h minus integral a to g of x, f of t dt, plus a to g of x plus h, f of t dt. Okay, now I use this notation. Okay, so you see that I'm not using any ideas here. The only idea I used was this was. Okay, so this was the brilliant idea. Introduce this notation. That's the brilliant idea. After that, I'm just trying to write everything in terms of that notation, just playing with the equations. So what is this? This is minus, okay. First of all, I have 1 over h. Then I have minus this thing. Well, that thing is f of g of x minus plus this thing, f of g of x plus h. Okay. So, okay, let me go over there and finish this proof. F of g of something is f composite g, right? So I'm writing f composite g evaluated at x plus h minus f composite g evaluated at x. I divide this by h. Okay, so this is precisely what I have here. f composed with g evaluated at x comes with a minus sign. F composed with g evaluated at x plus h comes with a plus sign. And I divide it by h. Okay? So in order to find the derivative of this, I have to take the limit of this as h goes to 0. But fortunately, I can recognize the limit of this as h goes to 0. This is f composite g derivative at this endpoint x as h goes to 0. Okay? So phi prime x is equal to f composite g derivative at x. I found the answer. But I would prefer if the answer showed up in terms of small f and big and small g. So how can I get rid of this big F? I try one more step and see if things get any better. So chain rule now. What does the chain rule says? Take the derivative of big F, evaluate it at g of x, multiply it with the derivative of g at x. So this is f prime evaluated at g of x times g prime x. Fortunately, I now recognize f prime. Okay, so f prime is small f. So this is f of x. Okay, so here f prime is f from the fundamental theorem of calculus, g of x times g prime of x. Okay, so conclusion. If I have integral from a to g of x f of t dt, and if I take the derivative of this with respect to x, okay, so sometimes since we have, even though these are dummy parameters, nobody attempts to take the derivative with respect to a dummy parameter, but just to be on the safe side, we use this notation most of the time, a to g of x f of t dt is f prime g of x times g prime x. Okay, before we give a break, check that if I have a to x f of t dt, and if I'm taking the derivative of this, I'm actually using this rule. Okay, I'm evaluating f at the function here, f of x, times I'm multiplying this with the derivative of this, which is 1. Okay, so this is the usual thing. Also, okay, so this is the last thing I'm writing. If I have h of x to g of x, f of t dt, if I want to take the derivative of this, okay, so this intermediate step you do only once in your mind, then you write the last step. So this is d dt of, or maybe I put the parentheses here. I want, now this is x. Derivative respect to x of some number a to g of x f of t dt plus some number h of x f of t dt. Okay. Now I know how to take the derivative of this. It is this rule. I don't know how to take the derivative of this because the rule says that the function must show up at the top. Well, let's see. I just turn this around, put a minus here. Now I know the rule. So I'll write one more step. Integral a to g of x f of t dt minus integral a to h of x f of t dt. Okay, so what we are interested in is the following formula. Okay, so the derivative, so this is the formula you can use if you need. The derivative of this thing is this side. Okay. No, I have this thing, right? F evaluate at this one. Okay. So I evaluate this at that point. F of g of x times g prime x minus f of h of x times h prime x. Okay, so these two things are the same. Okay, so this is the usual Leibniz rule, and you can use it if you need. You don't have to develop this every time you use this. Okay, the rule is simple. Okay, so this is the basic theory. You evaluate this function at the top function and take the derivative of the top function. Always remember that the simplest version of the fundamental theorem of calculus is actually a very special case of this. G of x is the function is x. The derivative of x is 1. That's why it doesn't show up in the fundamental theorem of calculus. If the function is down here, okay, then since you are going to turn it upside down, you need a minus sign. Okay, you see that this condition, this part is also obeyed here, because I evaluate, also see that I can apply it here. I evaluate f at x times x prime minus I evaluate f at a times a prime. But a prime is equal to 0. This thing is equal to 1. So the whole thing is f of x. Okay, so the fundamental theorem of calculus is a very, very special case of this Leibniz rule. Of course, you see that Leibniz rule is developed after you developed the fundamental theorem of calculus. So that's why you don't teach this first. Okay, but this is a mechanism. Okay, let's take a 10-minute break, then we'll continue with other more interesting things.